Well, hello, everybody. Welcome to Ask a Scientist, where in just a moment, three of my colleagues are going to do their very best to answer any questions you have about the subject of sound. If you are, during the program, if you would like to ask any questions, all you have to do is use the chat function, or the Q&A function, rather. If you would like closed captioning, just press the closed captioning button and select subtitles. And if you are joining us on another medium like Facebook or YouTube, unfortunately, we aren't able to see any of your feedback, but we're so grateful that you're joining us today. At this point, I'd like to invite all of my colleagues to unmute themselves, to show themselves, and to tell you what their least favorite sound is.
So, hi everyone, I'll start. Sorry guys. My name is Emily. My pronouns are she and her, and I actually have a favorite sound prepared, so I'll share that instead. It would be the sound of my cat and her purrs, and when she talks to us, I just think it's very sweet. So I love hearing her around the house.
My name is Chuck. I use he, him pronouns, and I'll share my least favorite sound. And that's the sound of fingernails being drawn across a blackboard, which I'm sure many people can relate to as among their least favorite sounds.
Hi, my name is Katie. My pronouns are she, hers. And I would say I'll start with least favorite sound is any sound that I can't identify, just really takes my attention and drives me crazy. But my favorite sound is definitely rain falling outside my window during the summer.
Thanks so much, friends. Now we're just getting started with getting some feedback and questions from our people attending, but I thought we might sort of warm things up with a couple of simple questions. Could the three of you each define a little bit about what exactly a sound is and a different way they can be made by a person?
Sure.
Okay, well, sound is a vibration or a wave traveling through the air, or a series of waves traveling with the air. If we didn't have air, we wouldn't have sound. You wouldn't be able to hear anything. Like, for example, in space, you can't hear anything because there is no medium, that is the air, for sound to travel through. So any kind of disturbance, whether it is a piece of a speaker moving back and forth to make the sound, that makes a wave in the air that travels through, and our ears are set up to interpret that wave when it hits the ear as a sensation of sound.
Sound is also a form of energy that can travel through anything that is made out of stuff. So it doesn't have to be just air. Sound can travel through the solids around us. It could also travel through any liquids or any gas.
One way that I, as a former singer when I was younger, used to make sounds was using my voice, as I am doing right now. So humans have vocal cords, which are multiple muscles that we have in our throat. And as we mentioned, sound is a vibration. So when a human is speaking, those vocal cords are actually vibrating together to get different pitches and decibels, as we will speak about later, that will go through a medium, as Emily and Chuck have been saying.
Thank you, friends. We're starting to get some questions. Gail personally feels that screeching tires are the worst sound. It's not really a question, but would any of you like to tackle the idea of why are some sounds so unpleasant to us? Any thoughts?
It's a really good question. I can at least get this started and say that the reason why we hear, especially with screeching tires, those really high-pitched sounds is because the object that is making that sound is vibrating very, very fast. So anytime there is that really speedy vibration, that makes our eardrums vibrate that fast as well, and we hear those very high-pitched sounds.
Also, to get into kind of a different kind of science, humans are very social creatures. So especially as adults, or when we get even just a little bit older, we've learned things that maybe cause a certain feeling in us. So when I hear screeching tires, I also think it's very unpleasant because I associate that with a car that maybe is in a little bit of trouble and needs to stop really quickly. So that is something that I have learned in my life could lead to something even more unpleasant happening.
Yeah, I just want to pick up again on this kind of associative or association that human beings make. Maybe there's a particular event that happened to you that was unpleasant, and a sound may be unpleasant simply because it subliminally brings that back. But there are kind of some sounds that are pleasanter to hear than others. There are soft, mellow sounds. There are harsh sounds that have much like with light, you can take a spectrum of the frequencies of sound. We'll talk a little bit about the frequencies or pitches of sound. And some of those frequencies can combine in ways that sound very harsh. And some can be fairly simple sound, like a sine wave, like a sound like this. I'm using a iPad synthesizer right here to generate a sine wave, which is very mellow. It doesn't have a lot of the what we call those upper partials or higher frequencies that add into it and make it harsh. Others do and have this kind of harsh quality to it.
Awesome, Chuck, and I love your little toy there for adding to things.
Yeah.
Nico wanted to know if sound could travel through the vacuum of space. Now, Chuck, you kind of addressed that earlier, so I'm going to challenge you to maybe tell Nico about sounds that we have picked up from other planets. I seem to remember.
That is true. The space probes that have traveled to planets like Mars, for example, do have microphones. We know that Mars has an atmosphere. It's only 1% as thick as the atmosphere. So whatever sound is occurring on Mars by the wind passing through the struts of the spacecraft or past rocks or so forth, we have been able to record, although they would be much fainter because of the air being less dense and less able to carry the waves in a way that a human being would hear. A microphone that's sufficiently sensitive can pick those up. Now, other things that people say are like the sounds of Saturn or the sounds of are really electromagnetic disturbances that have been converted into sounds by equipment. In other words, you can't directly hear electromagnetic energy coming from a planet, but we can convert those to sound so that we can experience that as sound. We've done this with black holes, as a matter of fact. They wouldn't emit sound in a normal sense, but you can convert the information coming to them in a form you can hear. Now, of course, you can hear also some of these spacecraft have passed through the rings of Saturn. They can hear the impacts or the hits that dust particles make. So you could hear sounds from a planet in that way. So there are several ways, both sound and not sound, that we can experience things as sound.
Awesome. Here's one from Gwen, who's 9. Gwen wants to know how loud a sound can get. And maybe if you want, you could go and do what are some of the loudest sounds that have ever been made on Earth?
So in terms of how loud a sound can get, I don't know that I can answer that, but I'll ask Chuck or Emily to step in. But I know in terms of how loud a sound a human can hear, we're talking about something, well, it's called about 130 is the number. Decibels is how we measure it. So decibels, kind of the easiest way to think of it, we've talked about sound traveling in vibrations or waves. And how big that wave is, if we were to picture it, how tall or how long it is up and down is what marks a decibel. So the more stretched out it is, the louder it is. So humans can hear about 130 decibels. And I know the loudest animal, it actually lives in the ocean and that we know, that we have tracked, and it's the sperm whale, I believe, that communicates in very loud clicks that go up to about 230 hertz. But I don't know what the actual loudest recorded sound is. So I hope maybe Chuck or Emily can help me out with that.
Yeah, well, as Katie mentioned, the unit of sound pressure, which we experience as sound intensity, is the decibel. And what those numbers mean, it's what we call a logarithmic scale, which means if you go up 10 decibels, you're going up 10 times in sound intensity, because the human being basically here on a log basis. That is an increase from 120 to 130 decibels is a lot more sound that is heard than the difference between 10 and 20 decibels. With that said, the loudest sound that's produced on Earth is a rocket launch, which is about 194 decibels. Now, there, of course, are safety considerations. So people are really interested in hearing about decibels. So, for example, I have a list here of noise levels. The loudest possible noise is, I think, about 194 decibels. Now, these get dangerous, of course, up above 100 and 110 decibels. You can 100 decibel sound, for example, would be a hand drill or an impact wrench, and regular exposure of more than 15 minutes per day risk-free permanent hearing loss in that. And then, of course, you get up to chainsaws, about 110 decibels, more than 90 seconds, a minute and a half per day can lead to loss. But just to give you an example of the loudest sound versus the softest sound, the ratio of the loudest sound that a human being can take, which is about 120 decibel, versus the softest you can hear, is a ratio of about 1 trillion to 1. That is 120 decibel sound, which would probably be an ambulance siren passing very. That's probably one of my least favorite ones as well. The ambulance sirens will produce a sound pressure at your ear of 1 trillion times as much sound as the softest possible whisper you can hear.
Awesome.
We'll also add, sorry, Matt, that I think probably the loudest natural sound on our planet has been a volcanic eruption. And I can't tell you which one it was, unfortunately.
It was Krakatoa.
But I also want to add to what, say it again, Chuck?
It was Krakatoa. And as a matter of fact, this is the anniversary. This would have been 1883, it occurred. And it was so loud, it was heard distinctly 3,000 miles away.
Cool. That's amazing. And I also just quickly wanted to add to what Katie said about whales. The fact that they can make such loud sounds means that they can communicate hundreds of miles apart from each other, which is incredible to think about. It's like talking to your friend that's 100 miles away. But they can do that because they're in the water and sound travels quickly through the water. And they also use very low pitched sounds to allow it to travel that far.
Awesome. All right. Faith asked, what is the hardest way for sound to travel? Because sound can travel through different mediums. So are there some that goes through easier than others?
Well, sound can travel through all of the states of matter, but it travels the slowest through, well, wait, let me say that again. It travels the slowest through gases. And that's because the physical molecules that make up gases are farther apart from each other. When gases condense into liquids, the molecules are suddenly closer together. So because I like to call them stepping stones, because the stepping stones for sound to travel through are suddenly closer together, that means that sound can travel much faster through water. So I'm trying to remember. The speed of sound through air is about 770 miles per hour.
160 miles an hour, yeah.
Okay.
But that's at sea level. If you go up about 40,000 feet, it's only 660 miles per hour.
Where the air is a little bit thinner, right? Sound can travel through water at about 13,000 miles per hour. And then sound can travel through solids, again, because the molecules are even closer together, at an even faster speed that isn't quite coming to mind at the moment. But it's even faster than 13,000.
Awesome. And just remember, folks at home, if you're ever hiking with a friend on Mount Everest and you're attacked by a Yeti, they're not going to hear your warning cry for slightly longer than they would at sea level. Okay, here's one from Prisha, who's 8. Prisha wants to know how many sounds are there, and maybe you could talk a little bit about frequency and especially the kinds of high and low sounds different animals can hear.
Well, I'll talk a little bit about frequency since I already started mentioning this word earlier. I'm sorry, I made that mistake. So frequency is how tight that wave is that we were talking about. So how quickly it goes up and down and up and down. And the more times it goes up and down, the higher the frequency will be and the higher the pitch will be. And the way we measure that is in something called hertz, which I was mistakenly saying earlier. So we measure frequency and pitches in hertz. And in terms of how many there are, I almost want to say as many as you can imagine, but or not frequency, but in terms of sounds, many different animals and everything in nature has its own sound. But if Chuck or Emily can maybe speak to you more about how many frequencies there are that the human can hear.
Literally an infinite number, actually within a certain lower limit and a certain upper limit. The lowest sound, what a hertz is the number of vibrations per second that you hear. So a sound that has 100 hertz, meaning that 100 sound waves are hitting your ear per second. And as Katie mentioned, the higher the frequency, then the faster the waves that are hitting your ear per second. The more waves hitting your ear per second, the higher the tone. So here, for example, on a little piano keyboard I have here, it keeps disappearing. But as I go up, those waves get closer and closer together, and you hear it higher and higher pitch. As you go lower, the waves get more and more spaced out. Fewer of them are hitting your ear per second, and the pitch goes down. So those are discrete notes, but anything that makes sound can generate at any frequency between the 20 hertz that we can hear, which is the lowest sound anybody can hear, up to about 20,000 in the case of very young children. Now, that upper range that people can hear tends to go down with age. So when you're really young, you might hear 18, 20 kilohertz or 20,000 of those waves hitting your ear per second. That limit goes down to 8, 16, 15. Most adults can hear 14, 13, but it tends to go down as you get older. And so you can't hear pitches that are as high. But your dog loves them because your dog has hearing range that goes much higher than 20 hertz, for example, as well as some other animals do. So it's an infinite number. And let's also not forget that these pitches can combine in different ways. You can have different kinds of waves, like you're familiar with the sound, the sine wave that's right behind me, the diagram here, that shows a sine wave. It's this even up and down thing. There are also square waves and sawtooth waves and so forth that are made of mixes of upper partials or frequencies that are higher than that frequency that mix in with the sound. So all the sound that we hear are really combinations of many, many different frequencies. There's literally an infinite number.
I want to quickly mention that, like, again, Chuck has that example of the sound wave behind him that goes up and down, up and down. Sound doesn't actually travel through the air like that. Instead, we use graphs like that to actually measure the sounds. So if we look at a graph like what is behind Chuck, we can learn the volume or the amplitude of that sound and also the note or the frequency of it just by analyzing the data of that sound.
Cool. Great job, everybody. Okay. Let's see. Riley would like to know, are there machines that can see sound waves or detect sound waves?
Yeah, there certainly are. A microphone, I think, is a simple example of that, of something that can detect sound. And then it converts it into, you know, I'm not going to know all the words to say. It converts it into some sort of electrical package, and then it pushes out through your speaker, and it makes your speaker vibrate in a certain way so that you're actually hearing the types of sounds that we're making, for example.
So the sound can travel through wires, for example. Go ahead, Katie, you were about to say something.
A different type of sound that we visualize is actually ultrasound, which I believe is on the higher end of frequencies of sound. I think that's why it's ultra. And we do use machines to detect ultrasounds, and we can use that to at least look inside human bodies and see and try and diagnose things or just see what's going on. And I think we use them to detect other animals as well that maybe can communicate at higher pitches. So an ultrasound machine would be my first example.
The ultrasound machine that women use during pregnancy, for example, use sound waves that, you're right, Katie, they are actually higher pitch or higher frequency than the ear can hear. But because of that, the wavelength, which is the spacing between each sound wave, is short enough to be able to detect small structures in the human body. It's a way of, it's a little bit like X-ray, except instead of using light, high energy light, it uses sound vibrations, which also travel through the tissues of the human body. And the way those different tissues respond and bounce back sound waves to the receiver tells you if there is a fetus there or other things that are in the body. So it's just another type of sound detector.
Awesome. Now, Nico had a beauty. We were talking earlier about how sound goes through different states of matter, depending on how packed the atoms and molecules are. Nico wants to know, will sound go through the state of matter called plasma?
Really cool question. The answer is yes. Sound would travel through plasma slower than it would travel through gases. Purely because, because plasma, the particles are even more spread out. It's also ionized. I don't exactly know what the ions, how that would affect how the sound travels, but it would travel slower through plasma.
On that note, something kind of very interesting has been done. The sun is high enough so that it actually has electrically charged plasma, that fourth state of matter in it. And we have observed sound waves traveling through the sun. In fact, a sonogram has been made of the sun, showing it if there are disturbances like solar flares that happen on the surface of the sun. Waves can propagate or travel out through that disturbance, much like sound waves that we're familiar with, causing the whole sun to ring like a bell, so to speak, but at very, very low frequency. Again, because of the different ways that sound propagates through electrically charged gas and plasma.
Now, Chuck, since you just mentioned a bell, I'm going to throw something out to the group. I noticed that when a bell is struck, it tends to make one sound. It gets louder and then softer. But why is it that some things just make one kind of pure sound? What's that all about?
The difference is what kind of a resonator it is. If a bell, we hear the expression "clear as a bell," and it refers to the fact that from the bell, you have a sound wave that's fairly simple. It's similar to the sine wave, and it doesn't have a lot of other sounds mixed in with it. Now, other materials that make sound vibrate not just at the one frequency, but parts of it may vibrate faster, parts may vibrate slower. And so you get this whole range of different frequencies that come from that. Like a human voice is actually a mixture of all different frequencies. My voice, for example, has low pitches, which constitute the major part of the sound. But when I pronounce a consonant like s, and so forth, that's very, very high frequencies. A bell concentrates most of its energy in kind of the one note, and that's why it's very, very clear. And it has to do with the way it's shaped, the material it's made of. Metals tend to be like that bells are made of, iron, copper, or whatever.
Cool.
And I was going to add, the concept of natural frequency is why we can break things like wine glasses with sound. So if you've ever seen a cool video of someone using a sound to break a wine glass, or even someone singing to a wine glass to make it break, it's because of that same thing. You're using the natural vibration, the natural frequency of that sound. And if you play that same sound at the wine glass really loudly, then you could possibly make it break.
Nice, Emily. That's exactly where I was going. Thanks for jumping on that.
Good.
And then I think we are just about out of time for today, but I want to answer with a question that, again, you might be able to sort of flesh out a little bit. Shelley wrote, her son is 6 and very interested in being a scientist. He apparently always conducts his own experiments and documents his observations of animals. Nice job. Documentation, super important. He, I think, maybe came in a little bit late, so he missed why we could not talk to each other through space, and specifically wants to know why people can't hear each other on the moon without radios. So if you wouldn't mind touching on that, but then also I'd love to hear your thoughts on what people would sound like if they were trying to talk on places that had different atmospheres, like Mars or Venus or Jupiter. understanding, of course, they would die pretty quickly. But let's hear your imagination.
Okay. Well, in terms of not being able to talk on the moon, as we said at the very beginning, sound requires a medium to travel through. Light does not. So light can travel very easily through the vacuum of space. It's not the same kind of disturbance, not the same kind of wave. Sound waves need that medium. It needs the air molecules moving back and forth and bumping into other ones, which then move, bumping into other ones, which then move. That causes the wave to move. You don't have the air, you don't have sound. The thing that is making the sound can vibrate all at once, but there are no air molecules to carry the sound. The way they communicate on the moon is they use the microphones, which convert the sound of their voice in the space capsule, which has air in it, to electrical signals, which are then broadcast via radio waves to mission control, and then or to each other via the radios in their spacesuits. So in terms of what would people sound like on other planets? Well, we used to do something, there's some safety things involved in this, but if you inhale helium and try to talk, your pitch, the sound of your voice is going to go way up in pitch because of the different kind of gas. Sound waves travel differently at different frequencies in different types of gases. Or another type of gas, sulfur hexafluoride, which I do not recommend, but that can actually lower your voice. So we surmise that in different atmospheric setups, like on different planets, your voice might be at a different pitch, and that would probably be the main thing. You sound like a higher pitch or lower pitch.
When I was little, I grew up on a lake and I was a very avid swimmer. And one experiment that my friends and I did was we would go underwater and sing songs to each other and try and see if we could figure out what songs we were singing. And it always sounded so strange and not like it sounds when we are speaking through air to each other. But if you can access any kind of experiment like that, it could be fun. Maybe try even just tapping around your home and seeing how far away you can get from that specific surface before you can stop hearing those vibrations traveling through whatever surface you're on. And you can test that with different kinds of mediums, which we were talking about earlier. So air is one example, water is one example, or maybe wood versus metal. So you can do those experiments on your own as long as you're being safe and you have a grown-up helping you, making sure everything's okay, and see how far you can make vibrations or sound travel. And always record.
All right, well, at this point, I'm going to invite my colleagues to say their goodbyes and to mute their screen.
Thank you, everyone.
And thank you all once again for joining us for another session of Ask a Scientist. We're so glad that you join us every week. Remember that every weekday we'll have at least 2 offerings for our visitors at home. And if you'd like to support our effort, you can do that by going to our website, specifically engage.mos.org/welcome. So from all of us here at the Museum of Science, thank you so much again for joining us and the MOS at Home, and have a wonderful rest of your day.